Hello, this is Paul from Tech. In this video, let's prove Theorem 1.4.1, which is the basic properties of matrix operations, arithmetic operations. And you see, this is quite important. Okay, so we do have a lot of properties of matrix arithmetic. So like addition, matrix multiplication, and the matrix scalar multiplication. Okay, and then we have addition, subtraction, like that. Okay, so look at it one by one. So the first, we have the assume all the operation holds. Okay, I mean the matrix size should be suitable for all the operations. And then I look at one by one. A plus B equals B plus A is commutative, right? So let's look at the name first. So the first is commutative. The second is associative. Okay, it's the same as the number system. And the third is associative, but for matrix multiplication. And then A times BC we can distribute it, right? So this is a Laffer distribution. Okay, see, very good property. This distribution. Okay, Laffer distribution or right distribution, and the F. Okay, that's their distribution, right? But it distributed to the subtraction, and here is distribution. Okay, all these distribution can you see, and the AB is scalar numbers. So I can put this big parenthesis to say all this, okay, right? A distributive. Distributive laws holds for all the cases. And then L is compatibility. So we have a name we call this compatibility. Why we call compatibility? Because because the associative is computable. Okay, it's compatible. It's consistent among the two operations. One operation is matrix scalar multiplication. Another operation is scalar number multiplication. Okay, see the associative still work, so we call it compatibility among the two operations. The last M, so we call it homogeneity. So here we call homogeneity. So what does homogeneity mean? Homogeneity means the product. If we look at this part, if A is 2, suppose, if we double the matrix and then we double the multiplication, if we double another matrix, so we still double the matrix. If we triple the matrix and then we triple the matrix multiplication, this we call homogeneity. Okay. So now look at it. So how to prove. So A, I will show a basic way how to prove. Okay, so later I will prove A. If A is true, B is similar. I'll leave for you. So C is a little complicated matrix multiplication. So I will prove C. D, the distributive, I prove 1. And then E is similar for D. So how about the F? Okay. I prove F here. Okay, so you can see F is similar with D, but we change the plus to minus. So the subtraction is defined by B plus the negative of C. So therefore, we can use D, okay, distributor. And then this is a negative. Negative means -1 times the matrix. So I can use the homogeneity. So therefore, for F, see. So how about the F? Let me simple put it here. Okay. I put the proof for F. I can use D plus M, the homogeneity, to prove F is true. Okay. See, here is the symbol. A times B minus C means A times B plus -1 times C. right? That's the definition. And then distribute. Okay. So distribute. We just see this is a matrix. So what do? Distribute. That's a distributive, right? We have a times b plus a times -1 times c. Okay, so whatever. Probably you can say it's like this, right? And then this -1 is a number k. So by homogeneity, this -1, the number, we can take out. Okay. Like you triple C, you triple the multiplication. You negative C, you negative the multiplication, which is M. So by M, so this equals plus -1, right? Plus -1 times A times C. Okay, you probably put a parenthesis, and this means AB minus AC. See, this is the proof. Okay, so for F, so F is true, right? So the same for GH for all the distributor. Okay, similar. You can leave all the proof for you. Just verify. L is quite obvious. Okay, so you just use the scalar multiplication of the matrix. Just use definition. But the M is not so obvious. So our proof is M. See, all the other I just leave for you. So now let's go to commutative first. And proof for a commutative. Okay. Commutative, which is A plus B. Commutative of the matrix addition, okay, equals B plus A. So first, okay, A, B should be have the same size. Okay. Now the question first, why? A and B should be has the same size. So therefore, do addition, we still get the same size. So we look at the two matrices, both sides. These are matrix. First, the size are the same, so they are probably equal to each other, right? And then we need to verify each entry, the corresponding entry are the same, right? So how do you describe, how to denote? So we can do this. We look at the general entry of the left matrix, which is A plus B. This is the matrix. And I, J, the general entry, should be equals, by the definition, this should be the general entry, this plus the general entry of B, right? Or probably you can say, I can use A plus B, whatever is the same. Can you see? I can just, or I can do this. Okay. So because A plus B and the corresponding entry all plus together. Suppose the general entry for A is Aij. Okay, therefore this should be Aij plus Bij is good enough, right? And then the two scalar number we can switch the order. We learned a long time ago. This is Bij plus Aij, right? And therefore this word, this is just the general entry of B plus A at the position of Aij. Okay, because Ij describe all the index of the row and the column, therefore this is true. Makes sense? This is the general way. So this is true. Because I see the size are the same and then the corresponding are the same. Corresponding entry are the same. Okay, so the same idea you can prove other identities. And then look at the C, associative. Okay, look at the C, associative, which is A, B, C equals A, B times C. Okay. That's associative of scalar multiplication. So this time we definitely have to look at the size first. Suppose let me say A is M by R. So B should be R, started from R, because see, A times B, right? So A is M by R, so B should be R by something. Let me say it's R by S. Is that okay? Okay, and then we look at B is R by S. So C should be something. Should be S by something. Let me by N. Okay, so C is S by N. So now we set up. And then look at the size. See the middle R cancel, RS cancel, so the left side. So here BC is R by N. And then multiply together should be M by N is on the left side, right? Okay. You just look at the size first. We put these together, the size should be M by N. Okay, the bigger final matrix should be M by N. Okay, so M row and column. The same look at the right side. What is AB? AB is M by S. And then C is S by N. Therefore, this final is the same size. Is M by N. Yes, good. The size are the same. And then we have to look at the general entry. The corresponding are the same. So this time we have to use the definition of matrix multiplication. See, now. The same, let's look at the general entry of A, B, C, I, J. Okay. This means the general entry at the ith row and the jth column. So how to find this? By the definition. By the definition of matrix multiplication. Of course, I have to see B times C is a matrix. So A matrix times another matrix. Okay, so look at the general entry at Ij. What is that? I have to use the notation, otherwise it's complicated. I use the notation. So K is the middle. K started from 1 to BC is R row. Okay, so A has a R column, therefore is from 1 to R, right? And then is the ith row of A, which is A, I, K, times we see BC is a matrix. Don't worry, okay, so this is just a matrix. So the jth column of the matrix is BC. The jth column, so that's K, J. That makes sense. This is the definition. Because the column of A is from 1 to the column of R, that's why K, the index is from 1 to R. This is the definition. And then one more time of definition. Now, I copy. And what is B times C? Okay, the same. We use the definition again of matrix multiplication. So what that? That should be another. See, I have to put the big parentheses. I use the summation again. So the kth row of B, which is a K. I have to use the index. This time, let me use L to describe the column. Okay, and then the jth column of C. I use C to describe the general entry, which is L and J. And so the index L should be from 1 to the column of B, which is S. Makes sense? Okay, so here, complicated, but it's okay. So we know the summation. Okay, and the summation we have very good property. The first property we can distribute. Okay, see, we can distribute A inside. Distribute A put there, which is a distribution. So I use the distributive. I distribute. So we have this summation case from 1 to R. Okay, sorry. So we have another summation. Another summation. L from 1 to S. After the distributor, I have A, I, K here, B, K, L here, C, L, J here. Okay, can you see? Now it's better, much better. So this is commutative. Okay, the summation has a commutative property. Summation you can switch. So that's go to here. So I get L, the first index first, and then is K later. And then it's A, I, K, B, K, L, C, L, J. This is a commutative. Of course, a commutative of the summation. Okay, and let's associate something. I put a A, B together. So now, now let's associate something. So this I just change another. Okay, change L is 1 and S, and then I put see A, B together. Is that okay? So I put a parenthesis here, and then times C. Good. So I can do this. I can put a parenthesis, and then this K start from 1 to R, A, I, K, B, K, L, parenthesis times C, L, J. What that is mean? This means just factor out, okay, all is distributor. Again, you know this is the distributor. And after this, we get something. What is here? If I put a distributor, we use distributor property of the summation. And then look at this part. This part A is the matrix A, the ith row. B is the L column. So the index from 1 to R. This exactly is the form of matrix multiplication, right? Okay, so I get it. This should be a matrix A times matrix B. Okay, what is the entry? I can get it. This should be, let me copy, should be the matrix of A times B at the ith row and the Lth column. Can you see? That one equal this. It's just the definition of matrix multiplication. This term, you see, this term just equal that term. They are the same, okay? Then times C, L, J. Now almost. What is this? Okay, this is a matrix. A matrix is the ith row of a matrix. What is this? Is the jth column of matrix. So therefore, this is a matrix multiplication again. Therefore, I have this matrix multiplication. So matrix is AB. I just see AB is a matrix. So this is a matrix. So this matrix just times another matrix C. Okay, so what do we get? Is the entry of the ith row and the jth column, and that's the definition of matrix multiplication. See, and that's the proof because I get a ABC associated BC or associated AB. The general entry are the same, right? The corresponding entries are the same. Therefore, that's true. Okay, associated is true. And look at one. How about the distributive? And almost the same, I think. Now, let's look at the left distributor. What is the number? Number D. Okay, so let's prove D. D is the left distributor. Okay, which is A times B plus C equals. So we can distribute. Imagine this should be A B plus A C Y. get the question. First, you can think about the size. So let me say m by whatever r. So BC should be has the r through, otherwise you cannot do multiplication. So let me say B should be r by, or you from here. So m by r. So B should be r by something. Let me say r by n. Okay, so A is B should be r by n. And then we can do addition, so C has the same size, r by n. So A is m by r, so C is r by n. Can you see the size is good? Because here, what do we get? This is m by n, the right size. You can do the same. Okay, this is also m by n. So the size are the same. And then we'll look at the general entry. We still have to use the summation definition. So we'll look at it. A times B plus C. The general entry of ij should be equals matrix multiplication. I see this is a matrix, so that should be summation, right? So the A ith row, let me put a K as the index, and then B plus C, the jth column. See, this is a matrix, and then the index K is the column of A, right? So from the first column to the rth column. And then one more step. So by the definition, okay, this is the definition, okay, of multiplication. And then by the definition of addition. So we have AIK times BKJ plus C at KJ. Okay, so the index K from 1 to R. And then now we can do distributive, right? So that's easy because all these are numbers. So I distribute. See, what do we have? After I distribute, I should have a summation K from 1 to R. A, I, K, B, K, J, right? And then plus A, I, K, C, K, J. Okay, and then I can break it down into two summation. Okay, these we call associative. Just associated the first term together. Associated this together. Associated this together. So we should have two terms. The first term is AIK BKJ. Okay, and then the index K from 1 to R, and then plus the second AIK CKJ K from 1 to R. Okay, so these we call associative of course, is of the summation. Okay, so associated into two groups or combine like terms. So what's the first? So now the first term is easy. By matrix multiplication is A times B at the ith row and the jth column. And then the second is A times C at the ith row and the jth column again. This is the definition. See? And then by the definition of addition, so this is exactly A plus B. A times B, A times C at ij. The definition again. Is this the proof? Yeah, definitely. So distributive. Okay, so A can distribute it to B and C. See, and that is the proof for D. And then one more. What is homogeneity? It's not so obvious. I have to take a little time. Okay, so to look at it if M is correct or not. So M is BC, 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 right? A is the scalar number. So the last is M. We call homogeneity. Okay. So like how do you say? Is A times B times C. Okay. So double the B is the same as we double the C matrix. Is the same as we double the matrix multiplication. Okay, so that's homogeneity. The double any B or C is just as double the matrix multiplication. So I can see just two ways. Okay, the first is this equal this. Okay, if it is the same, and then we can prove that this is also equal this. Okay, so we have a two-way to prove. We need to verify two. Okay, two equation. So I just verify one. I leave another for you. So verify A B times C equals A times B C. Okay, I leave another for you. So how to? So the first look at the size. I have to set up B like is M by R. So C is R by N is okay. So B is M by R. So C is R by N. Look at the size. So A is scalar number. So this is the same size. So the left. So the size of the matrix. This is M by N, right? This right size. Scalar multiplication. Now I change the size. The size is the M by N. So that's good. Okay, that's good. Now we look at the general entry. So we look at A times B times C. And then we'll look at IJ first by the definition. Again, I see this is a matrix. So there's A, B. This matrix is at the ith row, right? And then the matrix C at the jth column. So the index case from 1 to the column of B, which is the definition. Okay. And then one more time, scalar multiplication. What is scalar multiplication? Scalar multiplication means A times IK. This is the definition of scalar multiplication. Okay, it's the definition. So times C at Kj. So K from 1 to R. Now is three numbers. Okay, I think that should be easy. I can factor the A out directly. The three number, no problem. So the A, I can put it out, right? So now I have A times summation K from 1 to R. And then B, I, K, C, K, J. What is this? Okay, I'm parenthesis. And this is with somebody say distributed or factored out. This is the definition of matrix B times matrix C at the position of ith row and the jth column. Makes sense? Is this the proof already? Yeah, definitely. See, we see ABC equals ABC. Okay, so the A can factor out. That's true. So this is true. I'll leave others for you. That's the basic proofs. Yeah, thank you.